This is the Chapter 23 lecture outline. This is the last chapter of Unit 2. So this will be the last bit of content you'll have to know for the Unit 2 exam. All right, and this chapter is on light, astronomical observations, and then finally the sun. All right, we'll start with talking about different signals from space. We'll start with electromagnetic radiation. So visible light is only one small part of what we call the electromagnetic spectrum. So this spectrum includes things like, you may have heard of gamma rays before, X-rays, ultraviolet or UV light, then we have visible light, infrared, which is IR light, and then finally radio waves. And we go from high energy to low energy in this list. So gamma rays are the highest energy and radio waves are the lowest energy. So this is a nice picture to show you how small the visible light spectrum is on the total electromagnetic spectrum. So all forms of electromagnetic radiation actually travel at the same speed, and we call that speed the speed of light, and this is about 186,000 miles per second. So we also call this the cosmic speed limit because nothing is supposed to move faster than the speed of light. Now, light's rather interesting. Light can behave as two different things. So we can model light as either a particle, which would be like a tennis ball if I were to throw that across the room. That would be a particle model for something. Or it could act like a wave, depending on the circumstance. So in the wave model of light, the wavelengths of radiation vary. So radio waves measure up to several kilometers long in wavelength, where gamma rays have a much shorter wavelength, which would be less than 1/billionth of 1 centimeter long. And white light, we could say, consists of all colors of light corresponding to the colors of the rainbow. So something that appears black is actually absorbing all of the light that's shown onto it, so it's not emitting any color. So white is full of colors and black is the absence of color. Now the particle model is, we call a particle of light a photon, and this actually exerts a pressure called radiation pressure on matter. And shorter wavelengths correspond to more higher energy photons. All right, spectroscopy is the study of the properties of light that depend on wavelength. So this is when we're modeling light as a wave. So the light pattern produced by passing light through a prism or something else that could split the light is called a spectrum. I'm going to actually have a demonstration showing you a modern computer spectrometer that will actually use something called a diffraction grating to split the light, and you'll actually be able to figure out what different sources are producing what color. So I'll be showing you a demo. That'll be the final video for this chapter. So there's different types of spectra. There's something called a continuous spectrum. So this is produced by an incandescent solid liquid, a high pressure gas. So the easiest example would be an incandescent light bulb would produce a continuous spectrum, and this would be uninterrupted bands of color. There's also something called a dark line absorption spectrum. So this is produced when white light has passed through a comparatively cool or low pressure gas. And this appears as a continuous spectrum, but with dark lines running through it. This is a bright example of a bright line spectrum, and these will be the type that I'll show you in the demonstration. So these could be produced by a hot incandescent gas, and they appear as a series of bright lines of particular wavelengths with a large black swaths between them. So these are the bright line spectrums for hydrogen and helium. And believe it or not, these colors are produced by the relative locations of electrons within each of these different types of atoms. So what you could do is you can identify a substance if you could collect that substance's bright line spectrum. Like for example, if you were to take helium and you did an experiment over and over again, this would always be the bright line spectrum of helium. It doesn't change. All right, so why do we care about this in terms of Earth science? Well, most stars have a very specific dark line spectrum. So the instrument used to spread out light is called the spectroscope. The one thing that we have to worry about, though, when we're trying to collect light from a star is something called the Doppler effect. And this is the apparent change in wavelength of radiation caused by essentially a moving source of light. So we're on Earth, we're moving, a star is out there in space, it's moving. So there's going to be some Doppler effect that we're going to have to worry about. The easiest way to illustrate the Doppler effect is if you ever were standing outside and an ambulance was driving by you, you would hear the siren The sound of the siren would seem to change as it was proceeding away from you. That's because of the apparent wavelength of that sound wave coming from the ambulance changes slightly as it's proceeding away and moving with the velocity. So the same thing is true with any wave. So any light wave coming from space will have some Doppler effect that will have to be taken into account. All right, so there's two basic types of optical telescopes. So this is actually being able to view light coming from outer space. This would be visible light. So one is called a refracting telescope. So these types of telescope use lenses to bend or refract the light to produce an image. So light converges in an area, what's called the focus of a lens, and the eyepiece is a second lens used to examine the image directly. But what happens is that there's an optical effect called chromatic aberration, and this is because when the light refracts through these lenses, different colors, which essentially are different wavelengths of light, will bend differently as they refract through these lenses. So you always have to worry about chromatic aberration when you're talking about a refracting telescope. So refracting telescopes use lenses. A reflecting telescope actually uses a concave spherical mirror, or sometimes it's a parabola-like shaped mirror. Now there's no color distortion here because light is simply reflected. It doesn't have to pass through a lens like the refraction telescopes. So nearly all large telescopes are of this type. And that picture down there is showing you how large these mirrors can be if you're talking about relatively large telescopes. All right, another type of signal that comes from outer space would be something that you wouldn't be able to see with the human eye, and this would be radio-based astronomy. So how do you detect this invisible radiation? So sometimes you can use photographic films to detect ultraviolet and IR, or UV and IR wavelengths, but most invisible wavelengths do not penetrate the Earth's surface. So sometimes you would have to even use, there's such thing as sending a balloon out in space to collect. Well, it would be balloons in the upper atmosphere. So to collect different radiation coming from space, you can send rockets or even satellites are used to collect information from space. So radio radiation, though, so radio waves, they do reach the Earth's surface. So there's a type of telescope called a radio telescope. These are large because radio waves are about 100,000 times longer than visible radiation. And these are often made of a wire mesh. But they have poor resolution, but they can be wired together in a network called a radio interferometer. So this is a picture of a large radio telescope in West Virginia. So it's a huge parabolic dish, and then what happens is the radio waves come down to the dish, it reflects off the dish, and then it ends up hitting a couple of receivers that are on this boom coming off the top of the dish here. So now here's actually where the radio waves are being collected. This dish is just used to focus radio waves at those locations. But these things are rather large. Now some advantages of radio telescope versus worrying about visible telescopes. They're less affected by weather. They're less expensive. They can be used 24 hours a day. They detect material that does not emit visible radiation. And they can see through interstellar dust clouds. So this means dust in clouds. It's not actually a cloud, but it's dust and different particles that are in space. So if you want to think of a nebula, which is just a big concentration of different space gases together, radio telescopes can actually see through those because the radio waves will penetrate all of that material. This is a picture of another radio telescope. This is a telescope that's 300 meters in diameter, and this is in Puerto Rico. If you've ever seen the movie GoldenEye, it's a James Bond movie. The penultimate fight scene is actually on top of this dish. And if you didn't know I was a nerd, I just confirmed that for all you all now. And okay, we'll end this chapter with a few other types of telescopes that are being used. So there's a visible telescope called the Hubble Space Telescope. So it's an optical reflecting telescope that's actually in orbit around Earth. So it's orbiting like a satellite. It was launched in 1990. It can collect UV light that would normally be absorbed by Earth's atmosphere. And it produces something called ultra-deep field images. Another type of telescope that we have is the Compton Gamma Ray Observatory. It was launched in 1991, and it's responsible for the discovery of gamma ray bursts from stars. We have the Chandra X-ray Observatory, launched in 1999, and this observes black holes, something called a quasar, and high-temperature gases that emit X-ray wavelength electromagnetic radiation. It reinforced the estimated age of the universe to be between 12 to 14 billion years old. And then we have the Spitzer Space Telescope launched in 2003. This collects infrared or heat energy that's mostly blocked by the Earth's atmosphere, and it orbits the sun. And this is just a picture. It's a false color image, which means it collects data and then assigns colors to different values of the data that comes in. So it's actually not this color, but this is it's just a false color image of a supernova remnant that was captured by the Chandra X-ray Observatory. All right, moving right along to the sun. So the sun is one of 200 billion stars that just make up our Milky Way galaxy, and it's the only star close enough to the Earth to allow the surface features to be studied. Now, our sun is just an average star. It's not small, it's not large, it's just average. But its structure can be divided into 4 parts. We have the solar interior, the visible surface, which we call the photosphere, the chromosphere, and then finally the corona. And this picture in this slide shows you relative locations of all of these things. All right, the photosphere. This is called the sphere of light. It's the sun's, quote, surface. It's actually a layer of incandescent gases less than 500 kilometers thick. So just like an incandescent light bulb, the sun would give us a continuous spectrum if we were to look at it on a spectroscope. The photosphere has grainy texture, which is made up of small, bright markings called granules, and this is produced by convection. And we'll talk more about convection in the weather chapters in Unit 3. So most of the elements found on Earth also occur on the sun, where the temperature averages approximately 10,000 degrees Fahrenheit. Then we have the chromosphere right above the photosphere. It's the lowermost atmosphere part of the sun. It's relatively thin. It's a hot layer of gases, again, a few thousand kilometers thick, and the top contains something called spicules, and these are narrow jets of rising material. So this is a picture of spicules of the sun's chromosphere, so the lowest part of the atmosphere. Then we have the corona. That's the outermost portion of the solar atmosphere. It's very tenuous, which means we can't exactly tell how large it is. It's ionized gases in this region escape the outer fringes and produce what's called the solar wind, and temperatures at the top can exceed 1 million Kelvin. So the solar wind and the sun's magnetic field make bubbles called the heliosphere that extend past Pluto. All right, so the solar wind and its magnetic field extend all the way through our solar system, even past the dwarf planet Pluto. And this is just a picture of the solar corona, so it's very large, so it doesn't have fixed thickness. Some solar features that are interesting. One is a sunspot, and these occur on the solar surface. It has a dark center surrounded by a much lighter region. So the dark color is simply indicating a cooler temperature. So it's about 1500 degrees Kelvin less than the solar surface around it. And these follow an 11-year cycle. And the large spots are actually strongly magnetized. And pairs of sunspots have opposite magnetic poles, just like a magnet would. This is just a picture of sunspots. So you're going to see that the dark spot in the middle is just relatively cooler than the other spots around it. And even this lighter color here, that's sort of a mix between yellow and black, this is also a part of the sunspot as well. Some other solar features, we have plages. These are bright centers of solar activity occur above sunspot clusters. We have prominences. These are huge arc and cloud-like structures that fly off the surface. It kind of looks like an eruption happening, so this would be a solar prominence. We have solar flares. These are explosive events that normally last about an hour or so. These are the sudden brightening above a sunspot cluster, and they release enormous amounts of energy. These eject particles, and they reach Earth in about 1 day, and they interact with the atmosphere to cause what's called the auroras, or aurora borealis, known as the northern lights. So these are actually partially due to solar flares and also just the normal solar wind. So we have all these particles coming from the sun, and they're interacting with the particles in our atmosphere, producing an emission of different colors of light. So that's why we have these things in the northern part of our planet. That's the end of chapter 23.